Okay. All right. I think I'm
So you're ready now?
Yeah, sorry.
Okay. Shall I introduce you then?
Yes, please.
Okay. So it's a great pleasure to introduce Ewa Deelman, who is a research professor and a research director at the University of Southern California. Ewa is famous internationally for her work on scientific workflows. She's been working on this topic for many years with a number of contributions. And today she's going to talk to us about AI and science workflow automation. It's a great pleasure to host her talk at UCC 2020 in these unusual circumstances. Ewa, thank you very much for accepting the invitation. Thank you for being here. A little early for you also over there, I think. But
It's
we
not.
are looking forward to your talk. Over to
Oh,
you.
thank you so much, Rizos. And it's 8 o'clock here in California, so it's not too bad. The only thing is that my network connection was not working. I rebooted my computer 3 times, moved my setup to another room. So I'm a little bit hyper right now. So, but in any case, thank you so much for joining me. I really wish these things were done in person. I think this is the second time that Rizos has introduced me this year, and both times were virtual. So today, I really would like to talk to you about AI and science workflow automation, and basically think about how AI is changing our overall scientific workflow, and also how the automation that scientific workflows are providing can be improved with AI, and also can be leveraged by AI technologies. So if we look at the overall process of scientific discovery and exploration of scientific questions, we can see that at the top, we started off with a question that we want to ask, when will the COVID vaccine will be available? What's the best COVID vaccine? Then in order to answer this question, we have to research existing knowledge. So in literature, maybe talk to our colleagues, look at what other work has been done in this area. And then we form a hypothesis of what we think we're expecting from the results. Then we gather the resources that we need to do the exploration. So this could be collecting data in the field, or gathering computer resources to do the computations that we need, or both, or a mixture of these things. And then we perform the experiment and potentially collect more data, or do some simulations. We then analyze the data. We then interpret the data, look at it, see if we can understand it. Does it fit our hypothesis? What are the conclusions that we can draw? And then finally, we publish the results. And obviously, this is not a one-shot process. During the interpretation of data, you might decide that you want to gather some more resources to do your exploration. You might change your hypothesis. You might do some additional research. So it's really a very complex process, from posing a research question and then sharing the results with others. If we look at traditionally what people have been doing in terms of automating this process, they've been really focusing on the bottom part of the life cycle, on the gathering of the resources, the performing of the experiments, and the data analysis. And the rest of the cycle is very human oriented. So in my talk, I'll describe this, what's happening today at the bottom of the life cycle, what kind of automations we have used, in particular focusing on scientific workflows and the system that we have been developing, illustrating the types of topics through the system. And then towards the end of the talk, I'll reach back to this higher level question and the higher level cycle, and really see what are the technologies that are coming in today to help us with this part of exploration. If we look at the traditional, at the bottom of our life cycle, and we unroll it a bit, and we look at what's happening there in terms of the various steps that we see happening, you can kind of dive in a little bit more. And so here we see that first you might want to find the data sets that you want to explore. You might gather, provision computational resources, set up allocations or provision resources from the cloud. You gather your scripts or write some new ones that would analyze the data or do the simulations. Oftentimes you then put these scripts into an overall workflow so that you can organize these computations in a particular way that gives you the overall analysis. And then you execute that workflow on a variety of resources, including computational clusters, HPC resources, clouds, and so forth. During the execution, obviously, you want to monitor what's happening. Are you running the appropriate codes? Do you see any errors? You might want to recover from errors automatically as they happen. And you also collect provenance information during that execution. And then finally, you get your results. It could be models, images, some other types of data that then you can interpret as part of the bigger cycle. If we look at where automation has played a role, traditionally it has focused on the workflow execution and the workflow monitoring, providing fault tolerance and provenance and others. So in the next part of my talk, I'll dive in a little bit deeper into this part of the cycle and talk about the various technologies and solutions that people have used to support this automation. First of all, I wanted to comment though on why people are using scientific workflows for their work. And it's mostly because workflows are easy to use and reuse. They can, once you've written it, you can run it again. They can be portable across various platforms, so you can run your workflow on a laptop and then potentially scale it up to the cloud. They can be shared with others so that an expert can design a workflow and then share it with other colleagues, so the GRAs, the staff or postdocs to do the analysis. And obviously this is particularly important if you're looking at domain science applications where it does take a lot of expertise to formulate the workflows and the codes. So once you have that workflow, then you can leverage workflow management systems to optimize the performance and automatically execute the workflow on your behalf. They can also recover from failures. They can monitor the execution and debug any problems or help you pinpoint the problems so you can address them. And as the workflow goes along, it can record provenance information, so what data was touched, what computations have occurred. And it can, during that process of workflow management, it can apply various heuristics to also make the execution more efficient. And it can potentially also detect any anomalies during the execution so that they can be addressed. If we look at what are the types of applications that they use workflow management systems, so this is one application out of IPAC Caltech. And this application provides a service to the community so that scientists can come to the Montage portal and they can ask for a particular area of the sky from a particular telescope, and that image mosaic is created for them on the fly. So in this case, the data and the derived data products are available to a broad range of users. There's a limited number of small requests that the Caltech can serve with their own resources. But for some other larger requests, you might want to go to the cloud or to other high performance computing resources to perform the computations. Also, so the workflow technologies here provide you an automated on-the-fly workflow generation based on what the user is asking for, and the automatic porting to different resources and that are available for computations, and also the orchestration of data transfer. Another application that we have worked with over the years are from the earthquake science community, from the Southern California Earthquake Center. And there, the scientists want to ask a question: what will be the peak acceleration or earthquake motion that you see in a particular geographic area in the next 50 years? So this information is useful, for example, for building engineers when they design codes, building codes to which the structures need to adhere to. Disaster planners when they want to see where things are, where the vulnerabilities in the system, and insurance agencies when they set the rates. If you look at this image here, this is a map of Southern California. And on the map, you see the different types of little points which represent the different workflows that are being run to generate this large scale map. So in this case, the codes are being collaboratively developed by the scientists within SCEG. Then they're put together into these more complex systems. And then for the scientists, the ability to correctly connect these components is important. And then automating the flow of data through the components. So originally they were just sending each other emails, running the codes, sending emails that the data was ready. However, with the workflows, they can do it much more automatically, which is really important, especially if you're dealing with running so many computations. And they, again, because of the scale of the problems, the automated fault recovery and support for scalability are critical. And so, if, for example, in this application, which is has a mix of MPI and single core jobs, the scientists ran on two HPC machines in the US, one from NCSA and one from the Oak Ridge National Lab. And they ran the computations for 120 million core hours, which were about 40,000 jobs. And as part of this, the workflows managed 1.2 petabytes of data, and 157 terabytes of the data was automatically transferred out and for analysis, and then 14 terabytes were archived for the future. And so this type of computation only represented a small fraction of this map, focusing primarily on the Northern California region in this case. So even though you could be, so I give examples of where these applications are really like large-scale projects, but even single scientists can benefit from automation, and maybe particular single individual scientists can benefit from these technologies when they need to perform large amounts of analysis on large-scale data sets. And they would use these resources to automatically and workers to automatically adapt to the dynamic resources that are available for them. So in this case, let me retrace back a little bit. So this is work of Aria Gladstein from University of Arizona. She did this work when she was a PhD student. Her question was, how did humans spread across the world? And she looked at a number of SNP arrays in Jewish, European, and Middle Eastern populations, and also whole genome sequences. And then she used that information to trace back how the population has moved from various regions of the world to the others. She didn't have her own computing resources to do the analysis, so she relied on the power of an Open Science Grid, which is a distributed high throughput computing platform in the US. And with some help, she developed these workflows that then she was able to dynamically schedule using workflow management system onto the Open Science Grid resources. And she was able to do this automatically and achieve good performance. And she also needed to record to record how the data was produced in order to be able to do the analysis. So these were just some examples of workflow applications. And if we look at how the workflows are being constructed, we can define this process into 4 main parts. We could start at the top with a workflow template. So these are basically the steps that a scientist goes through in terms of what type of analysis they want to do. So they think about, I want to do a fast Fourier transform of the data, then I want to do some statistical analysis. So this is really capturing kind of the high level steps that one has in their heads when they're thinking about how to analyze the data. Having this high level description of the computational steps, they then look at the data that's available. They might reference metadata catalogs, and then they create a workflow instance, which is now this template, but it's populated with the actual data that you want to do. At this stage, usually workflows are also are still resource independent, and they basically just capture the scientific analysis that the domain scientist wants to do. And then these workflows are then planned by a workflow management system to be executed onto the resources that are available to the user. Once we have, and as a result of the step, we have what we call an executable workflow, which is now the workflow that has all the computation components, all the data described, and the computations are tied to particular resources, and the data is also tied to particular resources, so we know where we're going to access the data from. And then this description is given to the scheduling and execution system, and that then takes this description of a workflow and places it on the appropriate resources and coordinates the data movement and execution as described in the executable workflow. As a result of execution, we have new data products that are being generated, metadata and process information that then can be recorded in various libraries and in various databases, so that it is then available to others to adapt and modify to their will. So now I'd like to talk a little bit about the various stages of this workflow lifecycle and see how automation can be done at these various stages. So starting with a workflow creation, back in 2001, we were collaborating with Yolanda Gill and Jim Blythe, who are AI researchers at ISI. And we were working with a LIGO experiment. So this is the Laser Interferometer Gravitational Wave Observatory experiment that in 2016 has detected the first detection of a direct detection of a gravitational wave. And back in 2001, we were trying to figure out how to provide them with interfaces where they could formulate the request in a very high level, and then translate this request using AI planning techniques to an executable workflow that then could be to a series of steps that could be executed automatically. And so we presented this interface to the LIGO scientists back in 2001. And what we really found out from them is that they didn't like this type of high-level abstraction. They really liked what we showed them was under the hood, which you see on the right. They liked this formulation of a workflow with multiple steps that you can manage and adjust at will. And so they really want to have that type of transparency in what was happening. So this was our first foray into AI planning techniques, and we did not pick it up since, but maybe it's time to revisit. And I apologize, some of these slides, I don't know why they're not projecting correctly, but I don't know what to do. Anyway, so in the second phase of a workflow planning, we look at various things that the system does on the behalf of the user. So first of all, we often deal with a distributed execution environments. In this case, we need to know the details of the sub-infrastructure that we're going to be running on and tailor the workflows to that infrastructure. In some cases, the workflow tasks that as the user described them can be small. So we want to oftentimes increase the task computational granularity to make the workflow execution more efficient. In some cases, the workflows can be very large. So it's beneficial to reduce the number of tasks in these workflows, because otherwise we might overwhelm the execution systems that support the execution, so the data movement of the schedulers on the machines. And there are also other reasons to reduce the number of tasks, because there are system and network overheads when you're executing the applications remotely. So other solutions that you might want to do is to provision resources ahead of the execution, and then do more work on these particular resources. The data also needs to be moved oftentimes to the computation. So we want to do this as part of a planning process to decide how you're going to orchestrate the data movement through the environment. And in some cases, for performance reasons or others, computations, privacy reasons, for example, computations need to be moved to the data. So then you need to also take that into consideration and look at the trade-offs of moving data versus moving compute. So in the Pegasus workflow management system that has been developed in my group, we have done some of these optimizations. We have done different ways of task clustering, where you group tasks into bigger holes, and then the system manages a number of tasks as one. We can also collocate tasks on resources to get better efficiency. We've also have been structuring large workflows as hierarchical workflows. So you can have, you see this on the picture on the top right, where where you basically have a workflow within a workflow, and then so this workflow is being unrolled during execution, but at each point in the workflow, the system just deals with that smaller portion when it's being managed. And then we also do workflow reduction in case we see that already somebody else or from the collaboration, or maybe even the same workflow, has already partially executed. We can reuse these data that are already available, and then we have a smaller workflow that we need to manage on behalf of a user. So we looked at workflow creation, workflow planning. In terms of workflow execution, there are a number of challenges there as well, and there are a number of solutions that people have come up with along the years. In some cases, the challenge is that computations may fail within the workflow, and this is something that we have to deal with increasingly so, I think. The techniques that we've developed are to automatically checkpoint the workflow, automatically restart it based from the point of failure. When resources fail, we can also, for example, if the data staging site fails, we can also retry a different site or different resources to do the computations. We can pick different services to do the data movement or use different protocols. And oftentimes also we run out of resources, particularly of storage, when it gets filled up. So in Pegasus, we proactively clean up the data as the workflow is executing. So you can see on the right, as the workflow is executing, we're adding nodes to the workflow to clean up the data that is no longer needed, so that you reduce the footprint of a workflow during execution. So we looked at the different parts of a workflow lifecycle, and the automation really has been focusing on the planning and execution. However, I showed you a little bit of what we tried to do in the workflow creation arena using AI techniques. I believe that's something that could potentially still be revisited. Maybe other techniques that are coming online. For example, finding similar workflows would be useful in this case. In terms of reusability, there's been some interesting work by Kate Keehee out of Argonne National Lab and University of Chicago. She's the PI on the Chameleon Cloud project, and there they support the reuse and repeatability of experiments using integration of Jupyter notebooks with the Chameleon experimental containers. So they combine Jupyter's notebooks' ability to represent the experimental process with the complex environment that's provided, you see on the right, by Chameleon to build very complex containers that can include multiple switches, can be connected by multiple networks, all put together into a larger whole. And so then you can have this description of a container built within the Jupyter lab. You can name the containers, and then you can, for the integration with Zenodo, you can export these containers to this archive and get a citable and discoverable DOI, so others can reuse these containers for their work. Another thing, so this was an example where you build this container in some sense by hand, and then you provision the container on the resources. We can also think that we add this provisioning step, automate it, and add it to what the workflow management system does. So this is a graph showing, or image showing, that we can build this ultimate workflow management system that receives a workflow, and then it can provision resources for that workflow based on several pieces of information. Some of that information is, first of all, it needs to know what are the needs of these tasks in the workflow. So it would potentially query a workflow, a performance model that could be analytical, could be an AI model that has been designed. It then, based on this performance model, it would reach out to a resource provisioning system to provision the resources. Obviously, it might not get all the resources that it needs. So there might be some negotiation that happens at this point. And you might also want to, based on the resources that you've acquired, to then predict the workflow behavior on these resources. So again, performance models and at this point, maybe simulations also can be employed to do this prediction. So at this point, we have a workflow. We provision the resources based on the needs of that workflow. So then we can move on to workflow execution. So this is the part that's been the typical workflows do. So you execute the workflow, you monitor the workflow and the infrastructure at the same time, so that you can provide information to the user about what's going on in the system. In addition to that, once you're monitoring the workflow and you have these performance models that set the expectation for workflow behavior, you can also do anomaly detection. So you can compare what you see during the execution to what your performance models have predicted. So in the next few slides, I'll show some of the work that we've done in this area. Before that, though, I want to underscore that the collecting performance information during execution is actually quite complex. We've devoted a number of time, a good amount of effort in Pegasus to not only monitor the workflow, which we've done at the top with various daemons that collect information about the task execution, how much CPU they're using, how much I/O, and so forth. But we also have added monitoring of infrastructure, so integrating with the monitoring tools that are deployed on the infrastructure as well. So with integrating with network logs, the data transfer services, and tools such as Darshan and others that are coming back that can tell you the performance at a particular time of the infrastructure. All this has to be captured in real time and then put in various databases or other types of solutions or systems that enable you to then gather this information, correlate it, and analyze it in real time to be able to detect anomalies. So we see a lot of, once we gathered all this data from the executions, we do see a number of opportunities for using this information not only to pinpoint anomalies or to classify these anomalies, so figuring out where they're coming from, but also you can use machine learning technologies to make the workflow management system more autonomous. So we can also predict model performance and automate that part of the process based on the execution of the workflows. We can try to do this automatically. We can also employ the techniques to do workflow reuse recommendations, so when during the workflow composition, and many others. However, when we're dealing with these, trying to make things more autonomous and apply AI techniques, we do have a number of challenges. So data collection is a big one. So you need to be able to collect enough quality data and data that's balanced across various class representations. So if you think of collecting data about anomalies, you have to have enough of different types of anomalies. You need to be able to have enough of that data labeled or augment the data so that you can have a rich set from which to learn on. You oftentimes have to structure the data, normalize it or scale, transform it in a way that's amenable to the machine learning applications, and or potentially develop new techniques that do it more automatically. And it's not always easy to figure out which machine learning techniques are actually applicable to a particular problem. So here, I'd like to show some examples of what we have done in this area. This is work that's been led by Anirban Mandal from Renzi, with collaboration from others. And in this case, we applied simple ML clustering techniques to figure out if a particular workflow is destined for failure or if it looks like it's going to succeed. So Anirban has selected a feature vector that has a number of workflow relevant features. So for example, he chose to have ratios of a number of jump instances that succeeded to the ones that have been done. He looked at the job instances that failed versus the number of jobs that were done altogether. He looked at the duration of the jobs as in ratio to the number of jobs that succeeded, and the duration of the failed jobs in relationship to the number of jobs that failed. And then also the ratio of a number of job instances that succeeded to the total workflow jobs in a particular workflow. So based on these features and using the K-means clustering, he he took information from a number of different runs, workflows that had clean, so no anomalies, and workflows where we injected failures during the execution. And you could see that we have a clear clustering of jobs that are destined for failures, and the different calls represent the different anomalies that were introduced to the system. And then the workflows that have succeeded cluster also within a particular group. So it turns out that if you monitor the number of jobs succeeded to the number of jobs that have been done, and the duration of these jobs that have succeeded, and the duration of the jobs that failed to the number of jobs that failed, you can tell during the workflow execution with a good certainty that whether a workflow is destined for failure or success. So this tells you that that there is an anomaly in the system, but it doesn't tell you what type of anomaly you are looking at. So two of my students, Patricia Kraftrov and George Papadimitriou, has started looking at whether we can apply deep learning techniques to analyze the workflow executions and to be able to predict and pinpoint the type of failure that you see in the system. So these are Gantt charts from the execution of different types of workflows that represent, in red, you have a delay from the time that the job is ready to execute. These are mostly due to dependencies in the workflows. You have in yellow the delay of a workflow management system and managing the execution. Queue delay is in green, where you're waiting in a queue at a resource. And in blue, you have a runtime of the jobs. And so we collected this information for workflow under normal conditions and also with hard drive failures and network packet loss. If you look at how this analysis is done, it's actually a workflow in itself. So you acquire the data running Pegasus on using various types of workflows on the testbed infrastructure, where you can introduce anomalies. You then take the logs and you do some pre-processing on the data. You have to calculate the delays and convert the timestamps. Then you prepare the data for plotting. And finally, you get these Gantt charts that I showed you before. And we wanted to see if deep learning techniques that have been extensively used in image analysis would be applicable in this context as well. So the workflow further expanded into a typical machine learning workflow, where you split the data into a training set, a validation set, and a testing set. Then you do hyperparameter optimization to pick the best learning parameters for your particular task. And then you train the model to recognize the different classes of anomalies in your system. And then you test it to see if you actually got good results. So unfortunately, I cannot share the great results of this work, since our accuracy is still not really very good. So we're still fine-tuning the model. We are also collecting more data, so we believe we might need to have more of the data to do a better classification. So this is still a work in progress. However, we also looked in the literature, and Patricia has been looking at a number of AI papers, and we see that many of the papers that use machine learning have a very similar structure, where you have a data acquisition, you need to have some data pre-processing, splitting the data into these different training sets, and then in addition to hyperparameter optimization, in some cases, people do also selection of different neural networks. So this is an application that decides whether a particular X-ray image, chest X-ray image, shows signs of COVID or not. And in this case, and this labels the data according to that. So then you train the model and you evaluate it. So we see a clear progression of these machine learning workflows, and we think that the machine learning that these workflows can benefit from the workflows that and workflow technologies that we've been developing. However, one thing that we see in these workflows is that they are very iterative. So we see that during the data collection and pre-processing, you might need to visualize your data sets, make sure that it capture the objective of interest. Based on the learning step, you might change your learning method, so there's some iteration at this point as well. If you find that you don't have enough data, you might have to go back to the data acquisition, which is something that we're doing right now, an example that I showed you. And during the validation step, you might also want to, again, iterate back to the learning phase or to the data collection phase to make sure that you have a model that satisfies your demands. So, but once you have these models, they're actually pretty easy to use. So this is work by Kelsey Lamb, who's a high school student in Northern California. She did a summer internship with us and worked very closely with Patricia. And she's actually working in our group a little bit more this fall as well. And what she did is she looked at reusing existing models to detect whether somebody is wearing a mask and if they're wearing it appropriately. So this is the workflow again that has the data acquisition step. The data sets are available on Kaggle, people with face masks. You do some data pre-processing, you split the data. In this case, they didn't do hyperparameter optimization. They used the recommendations that are already posted by somebody else, and that worked well on that set. They trained the model, and then they evaluated, and they used our team members to show how the evaluation has worked. So these are pictures of various people in the group and the children, and you can see that in many cases the confidence of the algorithm is pretty strong, reaching the 99%. Here we have the confidence was not very high, and we think it's because we don't have enough pictures with people having hats on, and so you see the different types of results. But this is really to show that once you have this going, you can apply it very easily. However, we have to be mindful of the impacts that AI has on our environment. So this is from a paper that looked at the energy consumption and resulting carbon footprint of various AI training algorithms, and as compared to our daily lives. So this is the carbon footprint measured in carbon dioxide equivalent. If you travel from New York to San Francisco, you consume about 2,000 of these units. An average car, including fuel, using fuel for a lifetime, is about 126,000. But if you look at GPT-2, so the older version of a transformer, it consumed over 626,000 of these units. And this was just one type of model that was trained some time ago. The new version of GPT-3 has not been released in terms of the amount of training that's been done, but we know that it has 175 billion parameters as compared to the 1.5 billion that GPT-2 had. So this number has grown exponentially. So we need to really be mindful of the impact that we have with our techniques on our environment. So looking ahead, where we see we do see a growing need for automation. We see that our high performance computing systems have become much more complex and heterogeneous and have specialized data storage and other components, and they're becoming increasingly more faulty. So they look more like distributed systems, but they themselves are becoming more complex, where we see software-defined capabilities coming into play. We have programmable networks that now can be leveraged to do some of the computations. We have very specialized data storage. At the same time, clouds are being also used for science. They are very heterogeneous based on who the provider is, and they can be very costly. In addition to that, you also have the edge devices that are coming into the mix and neuromorphic architectures that are being used for ML. So the complexity of our environment is growing, so more automation is needed. We need to worry about automating things within certain constraints, such as the resource capabilities, the types of resources that we have, the time and the budget. The carbon footprint that I mentioned, I think, is also very important. And so in order to do that, we need to be able to collect and share information about application behavior and profiles. And in my group, we started collecting these ML workflows, both the ones that we're doing, but also from the literature. So others will be able to reuse. When we talk about the complexity, we need to also deal with this faulty environment. So we need more work on detection and attribution. And we also need to have more adaptive workload and resource management so we can adapt to these changes as they happen. So kind of popping back out, what is the role of AI and automation? So I think it does present us with new challenges in addition to the system complexity and resource cost. We have issues of trust and related issue of transparency and explainability and reproducibility. We can kind of think of, how do we know that what we observe is real? What type of tools can we use to have this level of transparency and be able to understand what's going on with the systems and potentially be able to reproduce? I think discerning the truth is becoming much more difficult nowadays. So these are examples where one is from the web on the left, where we have from this person does not exist.com, where you have these AI generated images of people that do not exist. You couldn't tell if this was real or not. On the right, I give GPT-2, so the previous generation of, it's not the latest generation of a transformer. The beginning of my paper that says it examines translational computer science and describes how this process of innovation has driven the development and adoption of a Pegasus workflow management system and what were the challenges for the project over the years. So this is my text, and then GPT-2 generated things that looked reasonable, maybe not the greatest writing, but it did talk about that. We'll discuss the evolution of Pegasus, the impact it has on the development of many other systems and the challenges it faced in the development of its successor. It clearly had a slant more to so it was trained more on business type of publications rather than academic. It talked about manufacturing of computer peripherals and computer industry and so forth. But I'll be curious to see what GPT-3 would have done. Maybe I don't have to write papers anymore. So if we look back again to the top, to the AI lifecycle, and can it take over scientific research? This is this graph that I showed you at the beginning is annotated by information that was available in 2007 and written up in the Science magazine. So in terms of doing research, you can leverage things such as the semantic scholar that extract information not only from text, but also from graphs and influential citations. You have other tools that help you browse scientific literature. In terms of hypothesis, you have a company that can keep track of thousands of variables and formulate new types of hypotheses. In terms of performing the experiments, you can do wet lab experiments on the cloud. In terms of interpreting data, the companies that create mathematical theories based on the data that you upload to their sites. And you have Cytomatic that helps you cite appropriate papers as you write your own. So this was 2007. Since then, we also have a lot of things that have happened. Things are moving very fast in that domain. So we have COVID Scholar that now has detailed evaluation and labeling of COVID-related literature. We have the latest AlphaFold success, and GPT-3 has come out as well. So really, if we look at where we are today and how our landscape, science workforce landscape is changing, obviously COVID has made a lot of changes for us, but I'm also asking myself how will, apologize, this is, how will this change in the future? So how do we create new human-machine interfaces? How we do reinvent ourselves in the area of automation? How will being a scientist be different in the future? Will we still need scientists? So this is, I think, a big question. And the last slide I want to leave you with is, sorry, I apologize, is really, how we're going to be working in the future. So when I think of that, I think back to the 2008 movie Wall-E, where they had lots of different social messages, but the one that I want to highlight here is the one that, technology was making us lazier. So there was an article that finding the remote was the only form of exercise. But really, it was not only this movie showed that we're getting physically lazy, but also intellectually lazy as well. So the challenge, I think, is when we use all these AI techniques is not to become intellectually lazy and actually start asking more questions and demanding more transparency. And one thing that, that kind of gives me hope, I came across this quote in a magazine and it was by Carl Spolster from Heidelberg that said, to be creative, you have to dislike being bored. And I don't think a computer will ever feel bored. So for me, I'm happy to leave the boring stuff to AI and do the interesting stuff myself. So I hope you get to do more interesting stuff as well. And I'd like to thank you for your attention.
So thank you very much, Eva. That was very interesting and very motivating in terms of asking questions and lots of interesting information. Let me ask people, I think there is a Q&A session on Zoom. It doesn't look like there is a question. I don't know if there are people who would like to ask a question.
Rizos, I would like to ask a question.
Yes, Ashik, please go ahead.
Yeah. So Eva, it was a fantastic talk. I really enjoyed it.
Thank you.
Thank you for your time and energy, actually. So my question is more about explainability, because you gave a hint that Pegasus could be eventually used for explainable kind of computations. We know that deep learning is more like black box like phenomena, whereas Pegasus, or the workflow that we do in Pegasus, is essentially we know what we would be producing in individual tasks actually. So how can we overcome that essentially black box model to actually infer explainability when we have to use Pegasus within deep learning workflows?
Yes, and I think, I don't have a very good answer to this question. I think that's a challenge that we all deal with, but I think we need to also insist that when people do create these models, they do put in enough information that you can explain what's going on within the model. The other thing that you could also do is to use automation to test the model under different conditions and annotate it to understand how it behaves. So in some sense, do some reverse engineering and figuring out what's going on. And I think the the workflow management techniques can really help you in some sense, because they can do this exploration and testing of AI workflows. They can, potentially they can be used for attestation of what's going on with machine learning and AI tools. So I do hope that we see more of that kind of testing attestation. So when we put the various models in our workflows, we actually know what we're doing and what's happening. We can also, if the workflows orchestrate these deep learning or workflows, then we should also record what data went into them, what decisions people have made to maybe, what data they did throw away, what data, what parameters they used, and so forth, so we can make the whole process more transparent.
Okay. So Rizos, can I ask another question if you please allow me?
Well, we have lots of questions, but yes, if it is, I think it's the last session anyway. And so, we have a bit of time. So please go ahead. I mean, if Eva is happy to stay a little
Yes,
bit
of
longer.
course. Yeah, no
Okay.
problem. Happy to.
Okay, so you mentioned iterative computing, and for iterative computing, we essentially need a kind of more tightly coupled data model, just like we have Hadoop actually. So now I know that Pegasus does not enforce a particular kind of data model or kind of underlying data system, because we could run computation in any environment. So how different is Pegasus than the DAG model that we have in Spark or Hadoop actually?
Well, so I think, you know, the descriptions that the scientists give to Pegasus are very explicit descriptions of what you want to run. So Pegasus doesn't, you know, replicate the tasks, or doesn't divide the data on behalf of a user. It really does what the user tells it to do. So it's, you know, you can mimic the model, other models in Pegasus, but it basically does whatever the user, however the user structures the computation, that's how it's going to do it.
Thank you. Thank you.
So
Excellent.
it might merge tasks together based on performance, but it doesn't do any other types of transformations.
Okay, now, Eva, can you see the Q&A at the bottom? There are some questions
Okay.
answered.
Yes. So I have a question. How far are we from provable explainability of convolutional neural networks, especially in the area of health diagnosis systems? Yeah. So I think we're very far away. You know, and I think, it's a challenge. So I think it's still for a long time, it will still be a partnership between a human and an AI system. And I do think that AI systems can help us maybe pinpoint areas where humans should look at. But I think we need to ultimately, you know, we're responsible for, especially in these cases that are very critical, we need to be very careful on how we apply these technologies. And I have another question. I hope it answered your question, Christoph. And we have another question from Luis. Thanks for the talk. You mentioned edge computing. How do you see the main constraint in management when enacting geo-distributed workflows? So I think that the challenge there is basically looking at what capabilities you have at the edge, and having that information when you decide what type of computations you can do at the edge, right? So what kind of network connectivity you have, what kind of storage, and what kind of power. So I think you need to this is, I think, much more complex than what Pegasus deals with today, but we need to be able to figure out what you can send to the edge, what can you do there, what needs to be processed in the cloud or data center.
Okay, so I have a few requests for live questions. Alan,
Okay.
do you want to go ahead?
Sure. So that very nice talk. You mentioned in it some, just glancingly, some topics related to prediction. So the bulk of this work and almost everything having to do with AI learning from training is reactive rather than predictive. So I have a particular use case in mind in which we need to adapt workflows in the context of renewable energy. Renewable energy has features of variability, but also of forecasting. So we can predict availability of power and predict optimal scheduling. So my question has to do with how you can apply these techniques in that setting. And I just want to observe that anomaly detection is essentially detection of a departure from a current expected state. You could apply the same techniques using redefining anomaly detection to be departure from a predicted state. So I wanted to know if you thought, if you given any thought to forecasting availability of resources and the applicability of these techniques in those settings.
Yeah, so that's an interesting question, and I have collaborators from ESNet that look at where we jointly look at predicting network performance, and so it's a little bit related to your problem in the sense that it's a hard thing to predict because of it changes so much over time, and we found that. We were happy when we did experiments in a kind of a controlled environment that we found the features that would be good predictors of this network performance. But it turns out that when we went to do the experiment in the wild, the features were predicted features were different. So I think it's a very hard problem, and understanding and getting a grip on which features to use, I think is a challenge. So I don't have a very good answer of how to approach it, except for do a lot of experiments and collect a lot of data so we can figure out how to approach this problem.
Yes, thanks. I think at minimum, we need to have features in Pegasus and related workflow tools that allow us to schedule based on forecasted capacity.
Mm-hmm, mm-hmm. Agreed. And, we do have, in Pegasus, at least the scheduling is pluggable. So you can plug in your own scheduler to make the decisions either during the planning process or the scheduling itself.
Thanks.
Thank you.
So, Omer?
Great, thank you. Thanks, Eva. That was a fantastic talk. So I just wanted to put this proposition and see what you thought of it. When do we get the GPT-3 equivalent for a workflow constructor? So what I do is I put in a number of papers, I put in some data sets, and I put in, I want you to find the COVID cure. When do we do, how long, do you think, can we really marshal all the stuff that we've done in workflows and create something like that?
I think if you did it today, it would be like a kind of Frankenstein thing. Okay. But I think what we want, and I think it's an interesting question. And again, these answers are I cannot answer with any certainty really. But I do think that we still need a human to discern things at this point. What's appropriate or not. What's what makes sense at a high level. Can we match the AI model to our physical understanding of the physical world and the equation of things that govern it? So I think we need to have much more work tying AI to the realities of what we do in the real world, I would say. And this is something that people talk a lot about, the difference between AI applied in the commercial world to the AI applied in science. It has to be much more rigorous, and it has to have that explainability, transparency, notions of trust. So until we have that and we have confidence that the models give us things that are accurate and trustworthy, then yes, I think we can play around with GPT-3 and whatever, but we need to have additional means of attesting the truthfulness and validity of what we're doing.
Okay, thanks. Just one quick follow-up, Rizos, if I may. So essentially, I was just wondering, if you construct a workflow and then get an AI algorithm to construct the identical workflow, it would be interesting to see what the commonalities and differences are, because so of course, I fully agree that the parameter space of something like deep learning would be so high to infer, but maybe decision trees or some other mechanism whereby you can actually trace what the AI algorithm is doing and put them side by side and see what the differences and common themes are. Just a thought, yeah, but very interesting talk. Thank you so much.
Thank you. Yeah, I mean, I was wondering, so what I did with GPT-2 was just to give it one of my papers, at the beginning of my paper, but I was wondering if I train it into more of my papers and other, workflow papers, would it be, how much better would it be? So, maybe I don't have a job writing anymore. And in fact, I think, publications, I think will have to change, because especially if we see the amount of COVID publications that's coming out, nobody can read them, only AI can read them. And if only I can really read them and process them, then maybe we should publish in a way that AI can best understand it. So it seems right now we are publishing, then AI has to analyze it and then give it to us, and then maybe we'll look at something. But why not give it in a form that it's amenable to AI algorithms?
Fascinating. Thank you. Wow.
Oh,
okay, radical. I know it's too early in the morning to be radical, but
no. All this is very interesting, particularly for us, for those of us who are in Europe, and we now have the time to get tea and think. So, Olga.
Yes, actually, this is sort of a follow-up of the discussion that we're having, and I just wanted to comment. So in some production scientific workflows that I follow, is that the teams that decide to migrate or to move to the machine learning sort of implementations, what they do implement are these validation steps. So essentially you are doing in parallel two things. You're doing the traditional method of processing and you're doing your machine learning. So essentially it's a way of them integrating these validation steps to cross-check the correctness, obviously, of the result. And then also that provides them with a level of interpretability, so to speak, for what is actually going on at every single stage. So it's just a comment that you were discussing.
Very interesting. Thank you. And I'd love to see an example of that. So,
there was a paper actually published for high energy physics explainability.
Awesome. Okay, I'll look it up. Thank you.
Thank you.
Okay, that's good. There is one on Q&A, I think, from Vincenzo, a new one.
Okay, if there is a rise in interactive machine learning approaches, do you see a possibility to integrate human interaction in this context? Yes, I think, interactivity will be, I think, very, very important. So the more we can integrate and think about how AI can help us in our scientific pursuits, I think the better. In some sense, there are also discussions that AI would, start off being like your GRA, and then it would become your postdoc and so forth, in terms of abilities. And people often talk about AI as being, you and your AI. But we see that, the success in science really comes from these larger collaborations, people working together on problems coming from different domains. So I do wonder how AI is applicable in that context. Can AI provide you with a knowledge that you don't have, more of this cross-disciplinary knowledge that you don't potentially have, or how it would behave when it is a shared capability across a group of collaborators? How do they build out an AI that helps them in their common goal, and one that is not only, now you see the AI is really like a pinpoint solutions, right? It does this or it does that, but it's not really an integrated type of system that has multitude of capabilities. So how do you compose the capabilities that you need based on what your collaboration is trying to do? So I think these are very fascinating things. And I'm coming really from the world of automation and workflows. I'm not I don't design new AI algorithms, but I think it's fascinating to see how we can leverage this technology in the automation of science context.
So, okay, thank you. I don't know if there is anybody else who is who wants to ask a question. So let me try to give a different question as a final one.
Okay.
What do you think is the potentially really negative side of relying too much on AI?
Yeah, I think there are lots of things that we need to really look out for. I mean, that it's just I think it can do societal harm in a sense that, to increase the differences between the haves and have-nots, people that have access to these technologies and people that don't. It already has shown in society to apply bias and that's, I think, very dangerous. Obviously, the more you put automation and AI-based automation in things, in control systems that control anything from our drinking water to power to whatever, to nuclear weapons, that can potentially go really badly. So I do think we have to be careful in how we apply these technologies. They're fun to do to as a recommender system for your Netflix movie tonight, but when you apply them to real situations, you really have to be careful and really know that you understand what's happening, and under whatever the modes of behavior that AI would implement.
Right. No, thank you very much
Okay,
indeed. I think, we have to be careful anyway. There is a positive side, there is a negative side, and we have to look at both of these at the same time. So thank you very much, Eva. That was really, really great talk.
And thank you so much for attending.
A big applause anyway. I mean, I don't know if I can make myself really convincing by doing this. Omer, I believe it's going to be online, the talk, correct?
It's already online. It's live streaming to YouTube. So
all right.
Excellent. So, thank you so much, Eva. Fantastic.
So thank you very much.
Thank you
very much, everybody.
Eva. Thank you. Hi, Ivana. Great to see you. Hi, thank you for having me. It was really fun. Thank you.
Bye-bye.
Thank you. Bye.
Bye.
Thank you also.
Thank you. Bye.
Oh, nice.